Another really interesting primitive that we have in cryptography is called traitor tracing. So here what we do is we are in the setting where, let us say there is a software and you purchased a copy of this software. So actually many people do this, even I mean it's on record, so let me not incriminate anyone, but this is a very common malpractice where people sell pirated versions of softwares and books and so on, right. So what you could do is, like, let us say I purchase a book and I make cheap copies of it and sell that, right. So the question is that if somebody uses their own privileged copy, like let us say that, so every software for instance comes with a license, right. So suppose, let's think of that as a secret key for for concreteness. So what does that mean? Let us say that I purchased something, so that means I got some secret key, obviously I have paid money, I will get some privilege from it, right. So I can watch, let us say I can log in and watch something, or I can use Microsoft PowerPoint because I purchased the license, whatever it may be, right. I can use Zoom for more than 40 minutes because I purchased the license, whatever it may be the case. Now suppose I share this license with all of you. Now it is a valid license, right. It is not meant to be shared, obviously, right. But if I share this with all of you, can I be caught? So this is called the problem of traitor tracing, and here the example I am giving you is a very naive one. So the one I am giving you is that I simply give you my key. So this is easy for anybody to trace, right, because if I give you my own key, then if any one of you sort of complains, then you can show the key and it is immediately traceable to me, right. But you could imagine doing some, you could obfuscate it, right. You could imagine hiding it in some very clever way so that it still works, but it cannot be traced back to me. Maybe I do some very clever thing like that. So what you would like to do is that, let us say that let's look for concreteness at encryption. So let us say there are n users in the system, each one has their own secret key, okay. If some subset of these people collude together and they create a new secret key, can this secret key be traced back to at least one of these guilty people? This is the question. Is the question clear? So the example which I gave of just me compromising my own key, that is a very trivial way of doing any pirating, right, because it is immediately traceable to me. But what we could do is, maybe we all can come together and create some new key somehow using our key such that it works, but it cannot be traced back to one of us, okay. And once you start playing with these schemes, many ideas come. I mean, for instance, if there is some additive property between the keys, maybe I can just add up all the keys, and maybe the algebraic structure is such that the ciphertext is still decryptable by the sum. For instance, if it is like an orthogonality test, I am just making this stuff up, like, but if it is an orthogonality test, right. So suppose the ciphertext is r plus m, okay, where r is some random vector that is orthogonal to the keys, suppose. Then if I add all the keys up, it will still be orthogonal and it will still decrypt. So this is just a made up example, but this is the idea. So can you have a guarantee that no matter what the adversary does. How many ever keys it corrupts, whatever fancy ways it has of constructing the new key, can you have a guarantee that I can trace back to one of the original traitors? Okay, this is the question of traitor tracing, right? So the detective can trace back to at least one of the guilty traitors, and yeah, this is also something that we know how to do. So this is another thing we can do in cryptography. Okay, so then another example is bitcoins. So bitcoins are very, very cool. I mean, genuinely the science is very cool. Uses some very interesting ideas from cryptography, distributed algorithms. Okay, so I mean, yes, so you use cryptography in various ways, but double spending is one of the interesting things that you have to prevent against, because it's not a physical coin. So why can't I spend it again and again? So there are some very interesting ideas on how you achieve that. Okay, yeah, it's underpinned by a peer-to-peer network, and these, so this is also a kind of a multi-party computation, like there are many machines and they work together somehow to create this. It's very, very interesting. Of course, we won't have time in this class, but you actually get a currency which people use, right? So I mean, again, if you think about it, it's very surprising. So there are so many things that a bank will provide. What all things? For instance, authentication. I mean, you cannot go and withdraw money from my account, for example. I mean, not much point there, but you cannot even if you wanted to. But what other things are there? Like if I transfer money to somebody, it should go only to that person and nobody else, and moreover I should not be able to use up that money again. It's gone, it should be gone, right? So this is another guarantee. So there are so many things that a bank will provide, so many services, but if you don't have a central authority, how will you even agree on who has how much money, right? You cannot even broadcast exactly, and even if you broadcast, in a huge network, there will be some transaction happening somewhere. At what point will I get information about that to update my record? So it's a very complex problem, but somehow using cryptography, actually you can have these bitcoins, and as you know, they are very popular, right? So yeah, very interesting ideas here. Another one which is one of my favorites is broadcast encryption. So this is let's think of I don't know, some TV broadcasting application. So I watch a lot of Netflix, so let's use that. So in Netflix, for instance, we are streaming movies, and obviously we only want to stream to the authorized users, not to everybody, right? So I want to encrypt the data stream. As I stream the data, I want to encrypt it. But once again, the question is, how do I encrypt it in a meaningful way for this scenario? So for instance, let us say half of you have subscribed. So should I sit and encrypt the same data stream for each one of you using each of your public keys? So this will be very inefficient in terms of communication, right? So the question that broadcast encryption asks is that if I want to sort of send an encrypted data stream so that only some subset of users can decrypt it, right, and others cannot, then and cannot also when they come together. So similarly to the previous example, so this is always a security that we ask for in cryptography, collusion resistance. So if even if there are a set of malicious users, they should not, it should not be that the sum is greater than the parts. So if I cannot get anything out of the if I cannot launch an attack on my own, it should not be the case that together we can somehow launch an attack. Okay, so I want this collusion resistance, and obviously there is a trivial solution which is, you know, I encrypt to each person, right? That certainly works, but it's inefficient, right? Because it's going to take, I'll have to duplicate that effort for each user in the system, and this is going to scale very badly. So the question is, can you do shorter ciphertext? And yeah, so again it's something that we know how to do. So it turns out that, you know, you can achieve ciphertext with order log n, of order log n. Alright, this is another one of my favorite examples. So zero knowledge. Okay, so how do you prove that you know something without revealing what you know? So today's class is just all about all this fun stuff. I mean, I have serious notes also, maybe next time. So this is one of my favorite examples. Okay, so when you see, generally how do you prove anything to anyone? You give them the solution and let them verify, right? That's how you write your exams also, right? So if you think of the traditional notion of a proof, it is always by communicating knowledge of something. Like if I want to prove to you that there are infinite primes, how will I prove it to you? By showing you the proof, right? So the question is here, can I prove something to you with zero knowledge? I don't give you any knowledge about the solution. And you know, the acute example of this is a Sudoku puzzle. Okay, so for concreteness, so this is a really fun example which I think it works for all ages. I mean, I show this to school children when I give outreach talks, you know, I show this in all my classes. It's a really fun thing. So what's the idea? Okay, so everyone I hope has played Sudoku. So it's a 9 by 9 grid. Right, so every row, every column and every subgrid has 9 cells, and you'll get the puzzle with some numbers already published, and you have to fill it up so that all the constraints, I mean every row, every column and every subgrid has the numbers 1 to 9, right? Yeah, good. So now here is my question. Okay, so my question is, I solved it first because I am the teacher, okay, so I get to say this whether that is true or not. So I now want to prove to you that I have the solution, but I do not want to tell you the solution because I do not want to spoil your fun, okay. So how should I do it? No, your idea does not work. So the idea is that you know, maybe we will pick some random cells and have the prover. So let's call the person with the answer the prover and the other person the verifier. So what he is suggesting is that maybe, you know, the verifier picks random locations and the prover gives those locations, but this does not work, right? So first of all, it is leaking the answer.
It only leaks a part of the answer.
But that is not zero. I said zero knowledge, right? Nothing. I want to leak nothing. This is the first thing. The second thing is there is no way for you to verify.
So you take up some other property like sum of all the rows, sum of all the columns, sum of all the grids, and you publish that way. All of these are.
But that sum is in fact fixed. It's summation I 1 to 9.
Yeah, so that is how you show that you have a solution that works.
No, without knowing a solution, I can publish that. Summation I 1 to 9 I can always publish. Without even having a puzzle, I can publish that. So the fun example that I like to show is using playing cards. Okay, so let us say that in this, so it's a randomized process, and in this you know, in this exercise we will use cards. So now think. Alright, so it is going to be hard to guess, let me show you. Okay. Okay, so what I will do is the following. So, you know, let me, this is my this is my Sudoku grid, okay, it's 9 by 9. What I'll do is that I'll place cards face up. I'll place 3 cards each face up for each entry that is given in the puzzle. Is it clear? I have a puzzle, right? So like here I have 6 over here, right? So I took 3 cards. So here the suite of the card is not important at all. So it's just I take 3 cards with the number 6 on it, doesn't matter what color and so on, and I place them face up. Okay, this is our first step. Anyone, either the prover or the verifier can do this. Everyone can check and agree that this is indeed the puzzle that is given. Okay, now what should the prover do? So I want to hide the solution. So what is one immediate step?
Place it face down.
Very good. So place it face down. Okay, then this way. And again there will be 3. Okay, so 3 face up, 3 face down. This 3 corresponds to row, column and subgrid. Now, okay, there are 2 things, right? So one is that you should not learn my solution, and one is I should not be able to cheat. Now first, there is also a third very important thing, which is the functionality itself, which is that you should be able to verify. So how can you verify? Now at this juncture, let us say we turn all the cards face down, okay, and the verifier makes bundles of rows, columns and subgrids. So I can pick out 1 card each, okay, for each row, each column and each subgrid, okay, and the prover should shuffle it, because the verifier has no reason, the verifier has no incentive to shuffle, right? So I don't want you to learn the solution, let us say. Actually no, that's not true. The verifier also has an incentive to shuffle. Let's get to that. So let's go step by step. So what will we do? So the verifier will start making packets, 1 for each column, 1 for each row, 1 for each subgrid. The important thing is that for each, let's go with column first, okay. Let's take a column. The important thing is that from each cell in the column, one of the 3 cards is chosen at random, okay. And then you make packets for rows and subgrids, and now what can you do? You can check if the numbers 1 to 9 have occurred. So first of all, let's just finish the protocol, okay. So the prover will turn over the cards which are facing up in each packet and also shuffle them, and the verifier can open each packet to see that all 9 values occur in each packet. So let's look at each question. So first question is, will you get convinced? I would say yes. If I am honest. So what does functionality mean? That if I am honest, I can convince you. So if I am honest, this will certainly convince you if I didn't cheat. Second question is, did you learn anything about the solution? No, you did not, because you just saw the numbers 1 to 9 in some random order. So you did not learn anything about my solution. And the third most interesting question is, what about the cheating prover? Why can't the prover cheat? Very good. It's because of this shuffling step that we did, where for each row, each column and each subgrid we picked a random card. See, if it were the case that all the top cards I was using for row, all the next cards for column and all the next for subgrid, then how could I cheat? I could place inconsistent cards, right? So it's easy for me to have one solution for rows, one for column and one for subgrid, right? So I can place inconsistent cards, but by shuffling that, this strategy gets defeated, right? So using this shuffling idea, you can ensure that I do not cheat with some probability. right. Now there is always, because it's a shuffling argument, there's always some probability that it works my way, but then how can you bring that down? Do it again and again, do it a few times, right. Then each time for the shuffle to be in my favor, this probability will degrade exponentially. Okay, so there was, I think, I hope at least that this is the last one. So there was one more example I wanted to show you. This is attribute based encryption. So here the idea is that I have files, I have encrypted access control. So that means that I encrypt my file against some access control policy, and I only want users who satisfy that access control policy to be able to decrypt this file. So for instance, each user can have various attributes, like you're all students at IITM, you're in CS or EE or EP or EE, for instance, right. You could have whatever, you joined in a certain year, various such things. So maybe the solutions to the assignments, for instance, I could maybe encrypt them against the following access control policy. Only students from IIT Madras who belong to this or this or this or this department and are enrolled in this course should be able to open it. And that is exactly what attribute based encryption means. So basically your key will contain within it the attributes corresponding to you. So the key generator will give you keys after verifying your attributes, right. And now if your attributes satisfy a given access control policy, then and then alone can you open this message. So this is actually weaker than functional encryption, but it's an important and interesting special case, which I think when you just see functional encryption, this doesn't fall out so immediately. So I wanted to also show this, and of course this will again hold, security should hold even if some set of users come together and try to collude with their keys. Okay, so I wanted to talk about how to build some of these things. I mean, my hope was to show you some very interesting and cutting edge things that we work on in cryptography. And the nice thing is that for each of these, right, we will be able to base the security of the scheme purely on solving some hard mathematical problem. So the problem of factoring will be one of our favorite problems. The second one will be discrete log and its cousins. These two are very interesting to us because you just based on the hardness of factoring numbers, you can build a lot of cryptography, not actually all the stuff I showed you, but actually most of it can be built using lattices. And in some sense my examples are also biased because I work in lattices and I work in these topics, and in some sense I have shown you the things that I sort of know most about. But we will get to lattices later. They are post quantum conjectured, post quantum secure. But for now what we will do is we will define some of these hard problems, and it's really very sort of cool that these very complex looking, very complex and surprising looking objects or primitives or whatever you call it can be built, the security can be based purely on the security of a hard problem like factoring numbers. Like I give you 200-bit numbers, I don't give them to you actually, I keep them to myself, I multiply them and I give that to you and I ask you to factor it, okay, and I claim that this will take more than the age of the universe or something like that, right. And I can show you that one of these like if you can if you can break my crypto system, this surprising something, then I can use you to break factoring, This is the kind of guarantee we will give. So, the security will entirely be based on a very cleanly stated problem, all these very fancy things, right. The security of it will just be based on the hardness of solving some one particular problem. So, let us end here, we are over time anyway.